Hello, physics students. Projectile motion can be one of those topics that can be somewhat challenging when you first start playing with them. So I want to give a practice problem to give you a little bit more experience. We're going to talk first about the classic projectile, which is any projectile that returns to the same level. So if you fire something on level ground, if something goes up in the air and it's caught at the same height, all of those examples of classic projectiles. So we can throw whatever object we want. We have a catapult in this situation, so maybe we're launching a pumpkin. We don't know what velocity we're going to fire it at, so we can just make up a number here. Let's say we're shooting it at 40 meters per second at an angle of 70 degrees. And I'm illustrating that you can throw any numbers in here. The object itself doesn't matter because we're ignoring air resistance, so the shape doesn't matter, the mass doesn't matter. It's purely the launch velocity and the angle that we're firing it at. So to start any projectile problem, remember our first step is to draw a picture. So we have our pumpkin that's going to be launched out of a catapult. So go up, come back down. It's helpful to indicate the angle and the magnitude of the velocity. From that diagram, we can focus on just the velocity for a minute, and we're going to find the components. So if we look at that right triangle, to find Vy, Vy is going to be the overall magnitude, the total V value times sine of theta, the angle, which is 70 degrees. So this would be 40 times sine of 70. In the x direction, Vx is going to be the overall magnitude V times cosine of theta. In this case, that would be 40 times cosine of 70 degrees. So I would encourage you to take a moment and calculate this for yourself. Pause the video and see if you get the same answer. So if you've worked out Vy, you should end up getting a velocity in the vertical direction of 37.6 meters per second going upwards, and in the x direction about 13.7 meters per second going to the right. And we can do a little mental check here. 37 is definitely larger than 13. This was not drawn to scale. If this is a 70-degree angle, it's going to be going much higher. This side is going to be longer than the shorter side of the triangle. So those two sides check out. Those magnitudes of velocity seem reasonable to me. Our third step is to solve for time. And so if we know that we're dealing with a classic projectile, it's going to return to level ground. And so at the end of our story, when it comes back down, delta y is going to be 0. So we can use our delta y equation. Delta y is going to be vyt plus 1/2 at squared. And we'll use this to solve for, we'll do a substitution. Put this in for delta y, and we're going to solve for time. So we're going to try and solve for t. 0 is equal to the Vy value that we just found, 37.6 meters per second times time, plus 1/2. We should definitely remember acceleration is acceleration due to gravity, so that's negative 9.8 times time squared. This should be in units of meters per second squared. Sorry, I left that out. Alright, so let me clean this up a little bit. If we have 0 is equal to 37.6 t. 1/2 times negative 9.8 is minus 4.9 t squared. So we have a t squared, t, and 0. I'm going to add this term to the other side here. So we're going to end up getting a positive 4.9 t squared is equal to 37.6 t. And if we divide both sides by that 4.9 t, then we can simplify this a little bit. T squared divided by t, the squared cancels out. 4.9 over 4.9, that cancels out. T over t cancels out. and we're going to end up with time must be equal to 37.6. Remember the unit was meters per second, divided by the half of the acceleration here, which would be 4.9 meters per second squared. And so that should get you a total air time of about 7.7 seconds. Just double checking, meters per second over meters per second squared is going to be seconds, so that's a valid unit for time. Now ultimately we're trying to figure out how far and how high and how fast this pumpkin is going to travel when it hits the ground. So for step 3, we're going to solve for the range first. I'm going to transition my color back to red so that you can track the main work here. This time we're looking in the x direction. How far is it going to go sideways? So we're looking for the range. Delta x is equal to Vx times time. Well, we already solved for Vx. That was the 13.7 meters per second. And we just found time was 7.7 seconds. And so when we multiply those together, we should end up with a total range of about 105.1 meters. So this is our maximum range. Now we're also asked to find the maximum height. So to find max height, I would generally go with your time-independent equation. We know that V final squared is equal to V initial squared plus 2A delta y. We're dealing with the y direction. That also tells us that A is going to be g, the acceleration due to gravity. And remember that at the max height, V is equal to 0 in the y direction. So we can say that the final velocity in the y, 0, is equal to the initial velocity in the y direction squared. That was at 37.6 meters per second. That whole quantity is going to be squared, plus 2 times a negative 9.8 meters per second squared delta y. Be careful, this is a 2 times 9.8, which is 19.6, or negative 19.6, as opposed to up here you had the half 9.8, which is negative 4.9. So if I transition this over here, 0 is equal to 37.6 squared minus 19.6 delta y. I'm going to add the 19.6 delta y to both sides. Now remember that those two numbers, the 19.6 and delta y, are being multiplied, so you can't just add the 19.6, you have to add the entire term. 19.6 delta y is equal to 37.6 squared, divide by the 19.6, and your max height then would be 37.6 squared divided by 19.6. Jumping back to units, that 37.6 was in meters per second, so on the top we would have meters squared over seconds squared. This is an acceleration, which is in meters per second squared, and so our final answer, the seconds all cancel out, meters squared divided by meters should be in meters, and you'd end up with a total value of about 72.1 meters. So this projectile is going to travel 105 meters horizontally. At the max height, it's going to be going 72.1 meters vertically. That was just to clarify, we're looking for the delta y at the center here. That's what we just solved for. Now the last question was asking what speed is it going to hit the ground with. And that's actually very easy for a classic projectile because this is symmetric. If it's going 40 meters per second up at a 70-degree angle, it will be coming 40 meters per second down at a 70-degree angle. So if I draw this below, this path should be symmetrical, where that was a 70-degree angle, this is a 70-degree angle. It launched at 40. It's going to be coming down at 40. We know at the max height it went up to 72.1 meters, and we know when it hits the ground it's going to be 105.1 meters away. So I hope this was a little helpful review. If you have any questions, please reach out.